Hello and welcome back. In our last video, we looked at procedures and macros. And this one, we're going into the world of the interrupt. The 8086 interrupt systems, to be specific. Let's look at a world without interrupts to start with. What happens is that you have an endless loop. As soon as the processor is reset, it starts execution of the code and it continues execution over and over again till power fails or there is an error of some kind, etc. Now suppose you wanted to connect a keyboard to the processor. So the user is typing in the keyboard and the processor is continuously executing its code. Now let's assume it takes about 20 milliseconds for the processor to complete one loop right from the start to the finish. So really what happens is, as part of this program, you also have a keyboard driver. And this keyboard driver is looking at the keyboard to see if a key has been pressed. And if it was a world without interrupts, the keyboard driver can look at the keyboard once every 20 milliseconds, for example, right? This is called polling. And here, the keyboard driver polls the keyboard once every 20 milliseconds to see if a key has been pressed. This is too slow for a human being. The human being, when he starts typing, and especially if they are professional typists, are much faster than 5 keystrokes a second. They are really fast. And it gets worse if you had to connect something other than a keyboard as an input to the processor. And if that was true, those signals could change even more swiftly. How would it work with an interrupt? So what happens is, as soon as the key is pressed on the keyboard, interrupt controller gets into operation. The interrupt controller could be part of the processor or it could be a separate external device. The interrupt controller in turn interrupts the processor. The processor stops whatever it was doing, services the interrupt service routine, and so that in this case the keyboard service routine, and then comes back to the main program. This is what would happen in the case of a world with an interrupt. But there are many kinds of interrupts. So the big ones are a hardware and a software interrupt. There are two big families of interrupts. In the hardware interrupts, there is a non-maskable interrupt and a maskable interrupt. We'll talk about each of them in a little detail. In the world of software, for the 8086, there are 256 types of interrupts possible. All right. So there's a hardware interrupt, software interrupt. Hardware is maskable, non-maskable, and there are 256 types of software interrupts. Let's look at the hardware interrupt. If you see the 8086 chip, the pinout diagram, you connect the maskable interrupt to the pin number 18 called INTR, the interrupt input pin. You connect the non-maskable interrupt to pin number 17. That pin is called NMI. NMI standing for non-maskable interrupt. So this is the way you would connect external interrupting devices, hardware devices, to the 8086. So what is the difference between the maskable and the non-maskable interrupt? As the name suggests, if it is you as a programmer cannot control when a non-maskable interrupt is serviced. As soon as a non-maskable interrupt occurs, the processor has to stop doing what it is doing, execute the NMI service routine, and come back to the main program. In the case of the maskable interrupt, you as a programmer can choose to mask specific interrupt inputs and re-enable them when you want to. I will give you examples of when to use maskable interrupts, when to use non-maskable interrupts. We'll now move on to the world of software interrupts. So the world of software interrupts is incredibly more interesting than just hardware interrupts. Remember, hardware interrupts, we had two kinds, NMI and the maskable interrupt. Software, we have 256 different kinds of interrupts. Let's look at what happens. First of all, the software interrupt is very simple to call. So as part of your program, if you use the instruction INT stands for interrupt, followed by the interrupt number. So INT 00 to INT 0FF is 256 kinds of interrupts, and you can therefore play with this set of interrupts to do what you will within your program, right? When the processor executes this, what happens is the INT instruction is interpreted by the processors during the assembly time, of course. It jumps to what's called an interrupt vector table. And the interrupt vector table occupies location 00 to 3FF of memory, of the program memory. The interrupt vector table contains the code segment and instruction pointer for each kind of interrupt. So we said there are 256 kinds of interrupts, therefore you must have 1024 bytes of memory location to store the interrupt vector table. That's why 000 to 3FF. When you have this, so the location 00 to 001, 002 and 003, these 4 bytes contains the vector interrupt vector address for interrupt type 0, and so on and so forth, right? So as soon as the interrupt instruction is executed by the processor, it jumps to the interrupt vector table, takes the CS and IP addresses, pushes the existing CS and IP onto stack, loads it with the new one, jumps to the interrupt service routine, executes the interrupt service routine, comes back here, continues with the main program. Like any other, you remember the procedures and macros, a similar operation here, but this time for interrupts. The architects of the 8086 have reserved a set of interrupts for specific users. Out of the 256 that we have, some are really reserved. So that's type 0, type 1, type 2, type 3 and type 4. The 5 bottommost kinds of interrupts are reserved for special purposes. One is type 4 is for overflow errors, type 3 is a single byte interrupt instruction, type 2 is for as a non-maskable software interrupt, type 1 is a single stepping, so this is used for debugging, breakpoint establishment, so on and so forth, and type 0 is a divide error. But each of them has a CS and IP address associated with it. Type 5 to type 31 is reserved for future use in subsequent families of processors, right? Type 32 to type 255 is free for the user. You can do what you will with these kinds of interrupts, right? So let's consider a non-maskable interrupt at this stage, typically maybe a reset switch or something like this. In this case, when you push down the switch, NMI pin gets an interrupt. What happens inside the processor as soon as it happens? The processor will complete the current instruction. It then pushes the flag register. So now in the case of procedures and macros, etc., the flag register was never pushed or popped. Only CS and IP were pushed in the, for a procedure. Here, the flag register is also pushed onto the stack. It then pushes the code segment and instruction pointer so that the processor can come back to the main program at the end of executing the instruction service, interrupt service routine. The IP is loaded from the word location 00008 hex. Now remember, this is the reserved interrupt type for a NMI, for a non-maskable interrupt. So you as a programmer must load the correct interrupt service routine vector at this location 00008 hex. CS is loaded from 0000A hex. So now you have the instruction pointer and the code segment, the new ones, into the processor. The interrupt flag and the trap flag are reset to 0. So telling the processor that it has serviced this interrupt and new interrupt can come in and be acknowledged. And the processor jumps to the ISR, the interrupt service routine, executes the ISR and then returns back to the main program. So let's look at interrupt type A, right? So it goes to interrupt driver A, executes the interrupt, does a IRET instruction, comes back, interrupt, then there's a second interrupt, interrupt type B. Remember this, similar to what happened in a procedure. There is one big difference, right? The processor needs to know when to come back, when it has finished executing the interrupt. Remember, now in the case of interrupt, we are pushing the flag, the code segment and the instruction pointer. All of this is managed by the magic of the IRET instruction, interrupt return instruction. This is different from the RET instruction that was used for procedures. What happens in the case of the IRET instruction? As soon as the IRET instruction is executed, all the ISRs must end with this instruction. That's number one, right? So if you do not have an IRET instruction in the end of your interrupt service routine, the processor can never come back to the main program. As soon as the IRET instruction is executed, it pops the flag register, the instruction pointer and the code segment to start executing from the old location in the main program. This is how interrupts are handled. This is true for both hardware interrupts and software interrupts. This is how interrupts are handled in the 8086. Brief recap. So we had non-maskable hardware interrupt, maskable hardware interrupt, and we had 256 kinds of software interrupts. You need to have an IRIT instruction at the end of your interrupt service routine. The location 000 to 3FF is reserved for storing the interrupt vector table of the 8086. When do you use what kind of interrupt? This is the last piece of this video. So non-maskable interrupts are used during power fail to manage power fails. When response times are critical, the processor must service your request. When there's a non-recoverable hardware error, possibly from a peripheral device, power supply, etc. It could be used as a watchdog interrupt. We'll talk about watchdogs later on, but it's a watchdog interrupt, and it definitely must be used when there is a memory parity error. That's a hardware error. In the case of software interrupts, primarily used by operating systems. So if you wrote in disk operating system, Windows, etc., they would use the software interrupts. It could be used as communication mechanism between two parts of a program. So during one part of the program, you execute software interrupt, and the software interrupt service routine does something in memory which the second part of the program can read from later on. Hardware interrupts are external, they really come from external devices, keyboards, mouse, disks, hard disks, floppy disks, DVD drives, so on and so forth. Right? So kind of, while you can imagine a world without interrupts, it is extremely costly both in terms of time and processing power, because you're going to do polling all the time. The system has to be very simple if there are no interrupts, and that's why almost all architectures of microprocessors have an interrupt service capability built into them. I hope you got a flavor for what interrupts are through this video. Tons of material out there to read again, and I urge you to do that. This is not a simple subject. You must go through them. I just taught you the concepts. Please understand each of those interrupt service routines, interrupt service requirements, and how you would use them as a programmer. In our next video, I'm going to be talking about a special device called the 8259, which is a programmable interrupt controller. And this is a peripheral device that you can connect to the 8086. So till then, don't let anything interrupt your reading. Thank you.